Welcome all. I'm Patio Plasma, physicist at Mountain Comma, and I'm a senior scientist at the Exploratorium in real life. And I run the Exploratorium Sim in second year. So the thunder will be loud enough to hear, but it won't be a problem. Okay, so as a scientist and a mountain climber, I'm really interested in lightning, and I've had some close encounters with lightning, and I'm still here to tell you about it. So let me show you some things about lightning. I want to start with this wonderful image, and you'll notice that there's the main channel here, which is quite bright, and it's actually striking a tree. But I want to point out to you that there are a couple of thin channels coming up from the ground and not connecting to the main channel. And those are called streamers, and they often accompany lightning. They can be dangerous in themselves, although they don't connect to the main bolt, and that there are these side channels up here on the bolt itself. So we'll have to look at those and their origin, what's going on. Oh, is that, the voice should not be cutting out. I can speak up a bit, and hopefully that helps. If it is cutting out, let me know, and I will try to cure it. Oh, yeah, I want good sound. Okay, so I have to confess at the very beginning that scientists do not understand the exact process by which electric charge is separated to create lighting. And so I will give you some of the scientific observations. Yes, so I'll give you the scientific observations that we know, but realize that we still have a lot to learn about lightning. Okay, we want to start out. Perhaps many of you live in areas of the world where there is a lot of lightning. This is a chart which shows you how much lightning there is in different parts of the world. This is a number of lightning strokes per kilometer squared during a year. And in San Francisco, when there's one lightning bolt, it makes the newspaper. That's how rare it is where I live. But if you live in the tropical land, you have to see these red colors, you get a lot of lightning. Yes, you don't want you or your mic to be struck by lightning. So, the most common type of lightning is portrayed here. It's called a negative cloud-to-ground lightning, symbol CG-. And over the whole Earth, 25% of lightning is cloud-to-ground. That's a good thing, because that's the kind that interact with people and our structures. That means that on the average, 75% does not directly interact with us unless we're in airplanes. And but it ranges across the latitudes of the Earth. At low latitudes near the equator, only 10% is cloud-to-ground, and at high latitudes, 50% is cloud-to-ground. So when they have a rare lightning storm in Norway, there's more chance that it's cloud-to-ground than it is at the equator. Now notice here, indeed, there are lots of side streamers, but one bright stroke, the direct stroke of the lightning. We'll learn about that as we go on. There's also ground-to-cloud lightning, and you can see immediately that it's different because it starts out as one channel and then spreads as it goes up into the cloud. So that's a fairly rare form of lightning. But it does happen, and you can see it. So actually, at the beginning here, this is a viewer's guide to lightning, things to look for. There's lightning that goes from one part of a cloud to another. Usually, it just lights up the cloud like a big light bulb, but here's one that someone captured where the lightning stroke went from one part of the same cloud to another, taking a line outside the cloud, which is rather interesting. And there's actually cloud-to-cloud lightning, rarest of all, where a bolt goes from one cloud to another. So indeed, we'll talk about the direction and the branches in the next little bit. So, and indeed, sometimes you can get a lightning bolt from the top of a cumulonimbus cloud all the way to the ground. And that is very often positively charged as compared to negatively charged. And it has a tremendous amount more energy. It can have 10 times the energy of the stroke that comes from the bottom of the cloud to the ground. So many of these are what are called lightning superbolts, and we'll learn about those in a bit. Okay, so what's going on here? By flying gliders into lightning clouds, and I once saw an advertisement at NOAA, National Oceanographic and Atmospheric Administration headquarters, looking for someone that had a bachelor's degree in physics, a glider pilot rating, and a parachute rating, because they were looking for someone to fly gliders through thunderstorms, and thunderstorms had the habit of ripping the wings off of the gliders. That's why you needed the parachute. And I'm not sure how much they did that, but now they use drones to fly through the clouds to find out where the charges are. And what we find out is that the top of the cloud is 90% of the time it's positive. There's a major negative collection lower down in the cloud at a temperature just below freezing. And then a tiny bit of positives at the bottom, and the ground underneath is the cloud is positive. So the lightning goes from these large accumulations of charge, from a negative charge here in the middle. That will be cloud to ground. It goes to the positives on the ground. We'll look at that in detail. Yeah, semiconductor. So the comment, yeah, it looks like a semiconductor component. PNP, yeah, just like a transistor. And the top of the cloud, where it is very cold, minus 40 degrees Celsius and lower, tends to have ice crystals and positive charges. Now, 10% of the clouds have the opposite. They have positive on the bottom and negative on the top. But I'm just talking about the most common distribution here. Okay, so these, you can see, we have the classic cloud-to-ground negative lightning here on the bottom, and notice how it forks. The branches tend to go down more than up. We have the lightning that comes from the top of the cloud to the ground with 10 times more energy, and we have the intra-cloud lightning here, from the pluses to the minuses. So, as I said, scientists don't know exactly how the charge is separated, but here is one of the two theories, and that is that over here, the lighter particles, the cumulus cloud has a big updraft, over 100 miles an hour, 160 kilometers an hour upward motion of the air. And that causes the small particles, the black dots here are water drops, the snowflake patterns are snowflakes, and they get moved upward towards the top of the cloud. But as the water drops hit the snowflakes, they can form hail, and these large particles here are a kind of hail called graupel, and it's kind of a reddish hail. And the particles become big enough that they're moving down. So those large particles move down, they collide with the snowflakes moving up, and in that collision, the graupel gets a negative charge, and the snow gets a positive charge. And the wind then separates these into positives at the top of the cloud and negatives at the bottom. The thing is, as the graupel melts, as smaller bits of graupel melts, it leaves behind the negative charge in the middle of the cloud here and continues to the ground without carrying the charge all the way to the ground. So there's some problems with this theory. Yeah. So graphel is a name for small hail covered with a layer of water. So sometimes you'll be driving along in your car, and there'll be little hailstones, tiny hailstones hitting your windshield, and when they hit, there'll be a splat, there'll be a spray of water. That was graphel. So here's high-speed motion pictures, and I haven't figured out how to show movies in Second Life yet. I may need Q to help me for next time so I can show you some movies. Here's what happens in a lightning bolt. For some reason, and this is another unknown, the charge in the cloud gathers, and it's not big enough to break down the air. But the air breaks down anyway. And as we'll see later on in the lecture, it's thought that that initial breakdown that triggers the lightning bolt may be caused by cosmic rays. That the cosmic ray breaks down the air and allows a lightning bolt to get started. And then what it does is it jumps in a straight line about 50 meters, 50 meters, and then pauses for 50 microseconds. Just pauses. And then it sometimes branches here and goes on for another 50 meters and pauses again. And this is called the step leader. It steps its way to the ground, occasionally forking. Yeah, like cracks in glass, indeed. And then when it gets near the ground, sometimes a positive stroke, a streamer, leaps up from the ground to connect with the negative stroke in the cloud. And when that happens, much of the charge that's stored in the cloud then drains out of this channel and goes to the ground and makes a tremendously bright flash of light. So because I couldn't show a movie, I made a lightning bolt for Second Life. So I'll run this a couple of times. And so here it is. If you watch to the left of the screen, you'll see a cumulus cloud up there. Here comes the step leader. It forked. It hit the ground. A bright flash happened. And a little later, there was thunder. So I'm going to run that again. And notice that after the main stroke, there was a second stroke. And that second stroke did not go down the side branch. It's called the first return stroke. And in fact, there's a step leader that comes down, a return stroke that goes up, a fast dart leader, it's called, that comes from the cloud to the ground again, avoiding the side paths, and then a second return stroke. So let's run it again. I stood a little close to the strike that time and got almost electrocuted. You could see my avatar respond. Okay, one more time. Here comes step leader, return stroke, dart leader, return stroke. And if you look at the grass underneath where the lightning hit, you'll see a pattern burned into the grass, which is called a Lichtenberg figure. And the lightning hits in the middle, and then the current spreads out across the ground, burning the grass and making this figure. So I must admit that was fun to make. Okay, back to the slides. So here it is again. The step leader comes down from the cloud. There's an upward moving positive charge. There's a return stroke, a dart leader, another return stroke, another dart leader, maybe another return stroke. So here's the deal. People want to know which way the lightning is moving. And here's something interesting. The negative charge of 90% of the lightning comes down from the cloud to the ground. It steps down one step at a time. The high-speed motion pictures can show that. When it hits the ground, however, the flash, the bright flash, moves from the ground up, even though all the charges are moving from the cloud down. But the flash, the draining out, it's like you have a tube full of sand with a cork in the bottom, and you pull the cork, and the sand starts moving at the bottom first, and the moving sand, the place it's moving, moves up the channel. And that moving sand represents the moving electrons. So that's where it's brightest. So the brightness moves from the ground up in most strokes, although the charges are moving down. Your human perception of the motion, however, is completely driven by illusory results. There's something called the Pulfric effect, that this lightning flash moves so fast your eye cannot see it move. But if you're presented with a flash that all happens at the same time, a line of light that all happens at the same time, and one part of it's dim and the other part is bright, your eye and brain perceive the bright part first. So you will see a flash of light move from bright to dim, and that's called the Pulfric effect. In addition, there's temporal perception. The center of your field of view, the point you're looking at, you see things there before you see them in the periphery of your eye. So if you're looking at the top of the lightning bolt when it happens, you'll see it move up. You'll see it move down, because you'll see where you're looking first, if it's uniformly bright and the Pulfric effect doesn't come in. If you look at the bottom, you'll see it move up. So we have to understand human perception to really understand what you see in lightning. And that's why we use video cameras. By the way, some people, and I have been one of them, have seen black lightning bolts against bright clouds. And that's actually an after image. You look at one bright stroke of lightning and it bleaches your retina. It's so bright and leaves a place in your retina in the pattern of the lightning bolt, which is now less responsive to light. And then the cloud flashes as a bright background with another stroke of internal lightning, and you see the negative after image of the lightning. And that's what creates black lightning. The return strokes have no forks. They just, or very few forks. So this is a picture. Sometimes some lightning bolts can have up to 30 return strokes stretched out over a good fraction of a second. And that means that you can take your camera and you wait until lightning happens. Now it's all over. And then you take a picture and you catch one of the return strokes. And that's what this photographer did. Saw the lightning, took a picture, and caught a return stroke, because they go on over and over and over again. It's how to photograph lightning. The other thing is, when the lightning step leader approaches the ground, what's happening is the negative charges are making the conductive ground positive. They're driving away the negatives from the ground and making it positive. And the ground positives get concentrated enough, they can actually leap upward toward the downcoming lightning bolt. And when these two connect, you get the main flash of lightning. The first return stroke is really bright and has many branches, usually pointed towards the ground, because the branches are full of negative charge and the ground is positively charged. So there's an overall force coming down. They don't always have to be down. They can go up. The average is down. And in an average lightning bolt, it might be 0.3 of a coulomb. That's a lot of charge. Over a short time, that's 30 kiloamps. That heats the air to 30,000 Kelvin, 60,000 Fahrenheit. That's 5 times hotter than the surface of the sun, and that's why the lightning is bright. Well, 6 times hotter than the surface of the sun. So that's why it's so bright. It's really, really hot. Right. So in fact, the positive bolt of lightning is actually positive charges moving up. Those positive charges, for example, on the top of the cloud, the positive charges might be a ice particle that has lost its electrons and becomes net positive. But the lightning strike itself can ionize the air. It can actually break apart water molecules into hydrogen and oxygen and ionize the hydrogen. In the spectrum of lightning, we see a hydrogen, spectrum of hydrogen, the spectrum of OH molecules, the spectrum of water and nitrogen ions. And those positive ions can move and do move in the positive stroke. So the question about the positive bolt travels upwards, it's not electrons, you're correct. So walking through the Sierra Nevada, here, the nice Star King is the name of the dome in the background. I saw this tree that was hit by a nice average lightning bolt, and as the lightning went through the wet cambium layer of the tree, it boiled away the water in that tree and blew off the bark. And so this is the result of an average lightning bolt hitting in the tree. And the question is, do the ions actually move? Yes, the ions actually move. And in particular, hydrogen ions, that's called protons, move very nicely, thank you. Now, what happens when one of those superbolts, when a large lightning bolt hits a tree? Well, in that case, the tree explodes. And so here's a picture of a tree that was hit by, we believe, by positive lightning from the top of the anvil. And so the voltage here is up to 1 billion volts, and it can have 10 times or more the energy of the average lightning bolt. So these can actually really destroy corners of houses or blow trees apart. You don't want to get anywhere near one of these giant lightning bolts. Yeah, so it turns out, Bergeron, in ice is not a very good conductor, but ice will conduct a little electricity, and the main charge carrier in ice is protons, because ice is made of water, which has a pH, which means it separates out into hydrogen ions and OH minus ions. A hydrogen ion is just a proton. It moves quite nicely, thank you, through ice. So there are substances which do conduct electricity by the flow of positives. So here's a little histogram showing the number of lightning bolts over here on the left over the total optical energy. Now, this is not the total energy. This is just the energy in the light flash. And this shows you it ranges here over 3 orders of magnitude. And so low energy lightning bolts are rare. The average lightning bolt here is a little over, it's a few 100,000 joules in the flash of light. But some of the big ones up here are 10 million joules. However, when you do the entire energy in the lightning bolt, it can be 5 gigajoules. That's the energy contained in burning an entire barrel of oil, and it happens in under a second. So the average lightning bolt's half a gigajoule, and that's 20 pounds, 10 kilograms of oil in a flash. And these big ones are quite energetic indeed. So yeah, a lightning bolt can hit a car, and I'll show you that picture in a minute. And this is just another, the power, the peak power in a lightning bolt. And look at the number of zeros in this peak power, 10 to the 11th watts, so 100 billion watts. And there's a lot of energy, and it's in a short time, and that gets the power way up. So don't mess with lightning. All right, so the U.S. has a series of satellites called the Vela satellites that look for nuclear tests in the atmosphere. And they are set to pick up any nuclear flash that's 100th as strong as the Hiroshima bomb. And they were shocked when they discovered that there was a nuclear bomb blast off of Japan. Um, oh yeah, so the question about how much energy there is in a lightning bolt, um, or an average thunderstorm. An average thunderstorm is putting out a lot of energy. I don't have that number, but it will provide power for a long time in an average thunderstorm. But back to the superbolts. So they saw the equivalent of a nuclear bomb going off the coast of Japan, and then they saw some off the coast of South Africa. But then, most worrying of all, they saw them in Ohio. And the Japanese or the South Africans having a nuclear bomb was worrisome enough, but Ohio? We don't want Ohio to have a nuclear bomb. But then they turned out the satellites were being triggered by lightning flashes, these superbolts from the top of clouds. And now we have satellites that actually look for them, and this is a map of the lightning bolts with more than 100 billion watts of energy, the superbolts, across the Earth. And they were originally thought to be only the positive ones, but actually some of the negative lightning bolts can have this power. So here's an interesting thing. It's called ribbon lightning. And when lightning happens and there's a strong wind, the first bolt happens with its forks, and then the next bolt happens, but it follows the ionization path of the previous bolt. So it follows the same path, but the wind is blowing the ions to the side. And so it's like a tenth of a second later, and then the wind keeps blowing it to the side. So each subsequent stroke happens moved to the side. One way to see this is when you're photographing lightning, have your camera set on a time exposure. Perhaps you're photographing lightning in a dark environment. And then sweep the camera right and left. This is a still camera, not a video camera. Right and left. And here's what a photographer did. He swept his camera right and left, and he caught one of the bolts while moving to the left, and then the others he caught. And you can see the pattern of repeated bolts, multiple strikes. And so sometimes you'll get a stroboscopic effect from lightning. And it really is strobing. It's going off maybe 30 times. So lightning is accompanied by thunder. Here, I'll play it again. Here comes the step leader. Return stroke. Dart leader. Return stroke. Thunder. In this graph, you can see that the peak frequency here is just under 200 hertz. Well, it turns out the depth of the sound, the deepness of the sound, the frequency of the sound, is inversely proportional to the square of the energy. So a more powerful lightning bolt has a lower pitch sound. It's like dogs. Little dogs, yap, high pitch yap. Big dogs, low pitch. Same thing with lightning bolts. And those super bolts, a normal lightning bolt might be as big around as your forearm, and it's a couple hundred hertz. A super bolt might be as big around as a dinner plate, and it runs at infrasonic frequencies. It's down at 20, 30 hertz. So what causes thunder? Well, the air is heated in 10 microseconds. The air is heated to 30,000 Kelvin. That makes the air over 10 atmospheres of pressure in this channel the size of your forearm. The air starts out expanding supersonically, up to Mach 9. But after 10 meters or a few meters, it's slowed down to a sound wave. So if you're close to lightning, and close enough, within 10 meters, it can blow out your eardrums. And so one of the safety things is, if you're near lightning, cover your ears. And it turns out the thunder, if the lightning segment is along an arc, if it points towards you, it makes a long rumble. The sound is stretched out because it takes time for the first part of the lightning to arrive, and the second and the third. But if the lightning is tangent to a sphere centered on you, all of the sound from that lightning hits you at once, so it's a sharp boom. So in the pattern of the sound waves, rumble, boom, you can get a three-dimensional picture, and scientists have done this. they have put microphones around the ground, many microphones, recorded the thunder, and used the sound to reconstruct the shape of the lightning strike. Well, of course, we all know that the reason what you use thunder for is to find out how far away the lightning was. So when there's lightning, and you start counting the seconds, and then when the thunder happens, you stop counting the seconds. And in Europe, it's every 3 seconds, it's 1 kilometer away, the lightning strike. And in the United States, every 5 seconds, it's 1 mile. The general rule of thumb is, if you hear thunder at all, head for safety. And it turns out that on the average, 80% of the bolts hit within 5 kilometers of a previous bolt, but lightning can strike 20 miles away. And 20 miles is about as far as you can hear thunder, for reasons we'll see in a minute. So if you hear thunder, go to a safe place. A safe place is inside a closed building. Don't get under a shelter with no walls. Get into a car, and don't touch the middle parts of the car. So this is why you don't hear thunder from more than 30 kilometers away. The air is usually cool up high and warm near the ground. And sound waves, when they head out towards you, the top of the sound waves in cooler air, and so it moves slower than the bottom. And so the sound waves curve up, and more than 30 kilometers away, the sound misses you. So when you see lightning, because lightning always creates thunder, but you don't hear the thunder, that's called heat lightning. And it just means very distant lightning. Ben Franklin is famous for doing the experiment of flying a kite in a thunderstorm. It turns out that historians don't believe he actually did that experiment. He did experiments collecting electric charges from thunderclouds, but probably not the kite flying one that you see depicted here. And it's good that he didn't, because the next person to do the experiment was George Richmond, and the spelling is correct there. He was struck and killed by something that looked like ball lightning. He actually had a wood carving artist sketching his experiment. He was flying a kite out of the window of his apartment in St. Petersburg into a thunderstorm. And lightning struck the kite, and the artist drew from what he saw, and he saw a bright ball of light leap from the string to the forehead of George Richmond, killing him. So, yeah, he was sketching. Yeah. Yeah, well, so he did use the key to collect electrical energy from a thunderstorm. And he had a lightning sensor using a lightning rod and a string, but the historians I was consulting thought that he actually didn't do the kite experiment. That's right, the experiment was success, but the researcher died. So you don't want to mess with lightning. If you've heard the thunder and stayed around, these two people here were standing on the summit of Half Dome during a lightning storm. This was not a good thing. They passed a sign like this one, which I see all the time: extreme danger from lightning. To avoid being struck from lightning, get off the peak. Even more, get off the ridge. Where the ridge ends, get off the end of the ridge, get down. Those people I showed you, oh yeah, they were high, but alas, they were killed by lightning. In fact, here's a picture of a lightning stroke hitting Half Dome where they were standing. This is not the very lightning stroke that killed them, but if there's thunder around, I will get off summits as quickly as possible. But I have to tell you, the previous sign was on the summit of Mount Whitney. I do have a picture of the sign that warns you as you go up Half Dome, but I couldn't find it in time for this lecture. So once I was mountain climbing, it had thundered stormed in the morning, and the mountain was wet in Colorado. And I did the hardest climb I'd ever done before. It's called 510. And I got to the summit of that peak, and there was no more thunder around, some little puffy cumulus clouds is all. And I raised my hands up in joy, and blue spikes of light came out of my fingertips, called St. Elmo's fire. And I immediately lowered my hands and started moving very rapidly away from the summit. And I think that the comment there that on Mount Etna in a storm, and when the umbrellas started to spark, they went downhill. That was a smart thing to do. That's what I did too. So don't mess with lightning. So here's an actual photograph from General Electric where they have triggered lightning. This is man-made lightning. And they're in the car, and you'll hear that it's the tires of the car that makes you safe from the lightning bolt. But you have to realize that this lightning bolt has just jumped 3,000 feet from the cloud to the car. It's not going to be stopped by another 6 inches to the ground. And in fact, in this picture, you can see where the lightning bolt continues from the car to the ground by jumping from the rim of the wheel over the rubber to the ground. And in fact, lightning superbolts, when they've hit cars, have melted all 4 tires and had all 4 tires go flat as the car plummeted to the ground. But the person sitting in this car is safe not because of the rubber tires, but because he's in a metal cage, and the lightning stayed on the outside of the metal cage. So cars, metal cars, are really safe places to be. Sorry about that, plastic car owners. Those Corvettes will not protect you. The fuel is inside of a gas tank that is full of fumes of gasoline and very little oxygen. So usually it does not cause an explosion. As was said about being on the summit of, or on Mount Etna, and seeing the sparks coming from umbrellas, the hair on your body, the hair on your head can stand up under a thunderstorm. The hair on your body can stand up. And I just love this word in English. So it turns out the feeling of electrostatics, of your hair standing on end, has a name, and it's called formication. You have to really watch that M in English. You don't want to replace it with an N. And formication comes from the genus of ant. Ants are genus Formica, and so formication was actually originally the feeling of ants crawling on your skin. And static electricity, perhaps you've pulled nylons and wool sweaters out of the dryer at the same time and felt that feeling of ants crawling on your skin. That's called formication. When I'm working with middle school children in particular, they like to learn that name. So when they go home and their parents ask them, "Well, Johnny, what did you learn in school today?" they can answer, "Well, Mom, we learned about formication." Okay, so here's how to be safe in lightning. If you're standing out in the open, you can get hit by the direct strike. An interesting thing is that 80% of the people that are hit survive with serious injuries, but they survive. But you still don't want to be hit by lightning. If you get near a tree, the lightning can come down the tree and jump through the air to you because you're a better conductor than the tree. And that's called a side flash. Lightning can hit the tree, go into the ground, and spread out over the ground and go through you. It can make 1,000,000 volts between your legs. The current will flow up your body, through your heart, stop your heart, and you die. Yeah, that's right. We just had a report from Paris where lightning hit a playground just today and injured people very severely. The other thing you might not think about is that lightning can hit a fence and travel along the wire of the fence and then jump to you. So stay away from metal objects, actually. And you can see, after the lightning strike hits over here to the left, the ground has been scarred. That's the ground current, and that ground current. And oh yeah, golfers are the main victims in thunderstorms. Okay, for example, these cows along a fence line in Colorado, the lightning hit the fence and jumped to every one of the cows and killed them. Just illustrating my point, don't mess with lightning. So here's the answer. The lightning safety position. Those lightning bolts were lightning bolts from electron motion. That was the question that was asked. However, you can actually, I didn't show, but you can also get hit by one of the streamers that comes from the ground, and those streamers are the flow of positive ions. And those positive ions can really injure you as well. So lightning safety position, feet together, you want them to be touching actually, crouch down, do not touch metal, and get 15 feet from other people. And that 15 feet from other people is because one of the effects of lightning is it stops your heart and your breathing, and perhaps someone 15 feet away will not be knocked out by the lightning and can come over and give you cardiopulmonary resuscitation. They can give you CPR. So spread out if you're in a group and crouch down. And this person, even better, is on a foam pad because he's from his backpack. I was in one of the worst lightning storms in U.S. history. I was in the Big Thompson flood disaster, camped out in a tent on the summit of the Continental Divide. And I had picked a lightning-safe place, I thought. It was in a bowl surrounded by higher peaks. And I set up my tent with my wife. And in that tent, we received 1 year's worth of rain in one night. We had continuous lightning. We each got as far away from each other as we could in the tent, assumed this position on our foam pads, and managed to survive the night. So that was, and then later at dinner that night, we had been eating, and I looked off to the east, and I said, this is really unique. There's a thunderstorm coming from the east, which doesn't happen that often in Colorado. And my wife said, oh, wait, there's a thunderstorm coming from the west. And what we didn't know until we read the scientific papers later, there was also a thunderstorm coming from the south. And all three combined over the mountain we were on. And dozens of people were killed in the resulting flash flood. So that was quite the camping experience. Oh yeah, and here's lightning hitting the ground and current spreading out. That's the Lichtenberg figure. It can happen on flesh too. So here's a Lichtenberg figure on human flesh. This person was hit. You can see the point where the lightning entered the body. And looks like it exited where he was sitting. And what the lightning did was it went down all the capillaries in his skin and exploded the capillaries. So this is the path of the lightning portrayed in exploded capillaries. That's right. Humans are more conductive than air. Here's a site down here which will show you live lightning strikes in the United States within the last 6 hours. And this particular one I've chosen is lightning strikes for May 20th, 2016 at 9 o'clock at night that happened within 2 hours, so between 7 and 9 p.m. This shows you all the lightning strikes in the United States. So it's really, really cool. Electric utility companies have sensors that record every lightning strike so they can know when their electrical utilities have been hit. And they make this data available to the public. Yes, I say humans are bags of salt water. Nice conductive bags of salt water. Now, here was an interesting thing. We thought we knew a lot about lightning, even though we didn't know anything about how it's made, until some people were photographing with modern high-sensitivity cameras during a lightning storm, and they photographed above the top. These are huge altitudes. This is 100 kilometers altitude. That's the edge of space. And down here at the bottom, 20 kilometers, that's the stratosphere. That's the top of the cloud. They photographed this bright ball of light coming out of the top of the thundercloud. And they named that a sprite. And now people are doing lots of studying on these bursts of light that come out of the top of thunderstorms. So in fact, in this picture here, look around. The light flash over here is a lightning storm, and above it, in red, there is a sprite. And the bright thing's the moon. And this is the bright thing. This bright thing here is Dallas. And so this is how a sprite actually looks. I take it from the space shuttle. The space shuttle is a great place to see lightning. Oh. And here are some more sprites. Once again, about way high in the atmosphere, up there in the mesosphere and the ionosphere. And on this one, also notice the dimmer purplish lower parts like roots and the bright red upper parts as the atmosphere, the thin atmosphere, is excited, just like a neon glow tube, to glow brightly. It's not neon, but it's like a neon tube. So here is what we've learned since these have been discovered. We found that they form over positive lightning or negative lightning. At first it was thought they only formed, and over here on the left, these form over positive lightning flashes. There's sprites, and sprite streamers, and sprite halos, and then way up at the edge of space, giant circles called elves. And over negative lightning, we get blue jets that streak out from the top of the cloud, and gigantic blue jets that turn red as they reach up towards the edge of space. These new forms of lightning are very interesting. And one of the interesting things that they discovered about regular lightning is that regular lightning is accompanied by X-rays. And so here's a graph from the step leader. Every time it steps, there's a burst of X-rays. Each one of these is one step in the step leader. So as this lightning bolt jigged and jagged towards the ground, remember, it stops for 50 microseconds between 50-meter jumps. There's a burst of X-rays. And here in Florida, they actually built an X-ray camera. Now get a load of this camera. It is made of lead. The walls are made of lead. It weighs several hundred pounds of lead. And in the front of it, there is a 8-centimeter diameter pinhole. That's 8 centimeters. That's almost as wide as your fist. You could put your fist through this hole. If it's not covered with lead, it's only covered with 1/3 of an inch of aluminum. So this is a pinhole camera. The pinhole itself is covered by a 1/2 centimeter thick piece of aluminum. This camera takes 10 million frames per second. It has 30 pixels, and it weighs 3/4 of a ton. And these pixels here are actually sodium iodide X-ray detectors. So they actually made a movie, which I can't show, but they actually made a movie of the lightning. And here's a still image, and these are the 30 pixels of the camera. The bright white one down here is the brightest part of lightning. So this is where the X-rays came from, where the lightning acted, the tip of the lightning bolt. It spread up the step leader a bit. The general fogging of the film here, there's no X-rays. These were made by gamma rays that went right through the lead. So this is one of the discovery images that lightning bolts not only produce X-rays, they also produce gamma rays. Yep, and the 2 pixels here are out. NP means the pixel is dead. Yeah, it is on YouTube. I'll give you some links later on. But knowing that So we have X-ray and gamma-ray satellites in orbit, and interestingly enough, these gamma-ray satellites were receiving gamma rays, and when they localized where they were coming from the Earth. And we expected the gamma rays to come from space as cosmic rays. And as they looked more and more with different spacecraft, they discovered the gamma rays were coming upward out of thunderstorms. And what happened was, between the negative charges and the positive charges in a lightning storm, it made a capacitor with a huge electric field between it. And for any free electrons, that electric field would accelerate those electrons upward to relativistic speeds. This became a particle accelerator, and these electrons gained 100 million electron volts of energy. And when that 100 million electron volt energy electron collided with an atomic nucleus, it emitted a gamma ray and X-rays that were up and were detected by a spacecraft. They also discovered that the tip of a lightning leader, this is the one that was discovered in Florida, also created huge voltage differences from the tip of the leader to space nearby, to the air nearby, which could accelerate electrons at 100 million volts and make X-rays and gamma rays. So those are the two ways that lightning can make gamma rays. So here we go. Not only do lightning storms make gamma rays and X-rays, this Fermi satellite had particle sensors, and they detected antimatter. That the lightning storm down here over the horizon in Africa made positrons, anti-electrons, that followed a magnetic field line out of the Earth through the satellite and back down to the Earth, where the positrons reflected from the... As magnetic field lines come closer together, they can reflect moving charged particles before it hits the atmosphere. And then the positrons came back through the satellite again. And so in the graph over here, you see the main burst of positrons and the echo. And they've seen hundreds of these events now. So we now know that lightning can make X-rays, gamma rays, and positrons, or antimatter. Yeah, that's right. Where do people learn about positrons? They learn about it in Star Trek. Okay, well, lightning also accompanies volcanic ash clouds, and there's two kinds of lightning in volcanic ash clouds. There's lightning that occurs as the ash comes up out of the ground. Just instantly, as the ash comes out of the ground, there's lightning flashes. But then, after some time, deep in the cloud, there's things that look like more normal cloud-based lightning strikes. And so we think that these are really two different electrification processes. There's something about the ash moving through the conduit up towards the surface that ionizes the particles of ash. And then, with water vapor condensing and interacting with the ash, you get a more normal lightning bolt. Yeah, that's right. Yay, day, I finally got to geology! And so, for example, here's the volcano Sakurajima in Japan, and you can see the lightning here accompanying the molten rock, just spurting right out of the ground. This is the first cause of the lightning. It's charging based on the motion of the magma and particulates through the channel. I doubt that there's much water droplets involved in the source here of this lightning. That's incandescent lava there, a little hot for water drops. So we have a lot to learn about geology of lightning bolts. Here's another one. Again, you see here the instantaneous lightning and the lightning from higher in the cloud up here. Two kinds of light. Now, there's reports of lightning bolts in dust storms, but for the life of me, I searched and searched and searched, and I could not find a picture of a lightning bolt made by the dust. There are pictures of lightning bolts in dust storms, but dust storms can also be kicked up by cumulus clouds, by thunderclouds. So I never found a clean one where it was just lightning in a cloud. However, I did find this one of rotor blades moving through dust in the desert and electrifying the motion, the static electricity of the blades striking the dust particles made enough electrical charge that it made electrical discharge. Yeah, that's right. The comments are yes. Not only do you want to avoid volcanic eruption, you want to avoid the lightning in the volcanic eruption. But however, NASA did detect lightning on this very dust storm on Mars, right here. They detected lightning, and they detected lightning because lightning is accompanied by radio waves as well as gamma rays and X-rays. So they detected the flash of light on Mars and the radio waves. So here's a case where there was no cumulus cloud in the vicinity, and where dust actually made lightning. That's right, the Urey-Miller experiment, and that comes up in my next slide. The comment was, what about the Urey-Miller experiment, that lightning helped create life on Earth? Well, this is a picture taken of the clouds of Jupiter at night on Jupiter. And the clouds in this picture are illuminated by light reflected from the moon of Jupiter, Io. And the bright spots in here are lightning on Jupiter. So these dots in this picture are pictures of lightning flashes on Jupiter. And when we study the altitude from which those lightning flashes came, we find that they came from the place in the Jupiter cloud where liquid water drops could exist. So we think that these lightning bolts are similar to lightning bolts on the Earth, but we're not totally sure. And as the audience commented, here you have compounds, you have water, perhaps you have other compounds, and lightning. The lightning takes apart the methane, perhaps, and the hydrogens and the carbons reassemble into organic molecules, perhaps the origin of life. Yeah, I really liked, you can go online and look for Julia Child doing the Miller-Urey experiment. And she actually makes primordial soup, she calls it, and holds it up and says, "Bon appetit!" One of my favorite ever YouTubes. We've also seen lightning on Saturn. There was a huge storm on Saturn that happened in the northern hemisphere here. By the way, this blue line is actually the plane of the rings, edge on, and the black here is the shadow of the rings on the planet itself. But up here is a giant storm, and that giant storm lasted for almost a year, over a year, and the winds of Saturn spread it around the planet until eventually the tail of the storm impacted the storm itself. So like the great worm Ouroboros, the storm ate its tail and died. But during the storm, there were flashes of lightning on Saturn, and that lightning came from a level in Saturn that had water droplets in it. So the lightning here was made by water drops. And Miller-Urey experiment, maybe it's making organic compounds. Yeah, so, but at different elevations in the atmosphere, like on Venus, there's lightning on Venus. I couldn't find a picture to show you. And the level in the Venus atmosphere where lightning happens, it's 50 miles high in the Venus atmosphere. And at that level, you have Earth atmosphere temperatures. In fact, NASA says if you fill a balloon with Earth air in the atmosphere of Venus at that altitude, because the atmosphere of Venus is carbon dioxide, Earth air is like helium. It will float. You could live inside a giant blimp on Venus. Sorry, on Venus. And floating 50 miles above Venus and be comfortable at that temperature. And there are levels in the atmospheres of Jupiter and Saturn that have good, comfortable Earth temperatures. Well, here's another picture of Saturn lightning taken at night on Saturn by the Cassini spacecraft. Well, I want to finish with just two more slides. I'm going to finish right on time. There we are. So one new theory about why lightning was created is that the ball of charge in the atmosphere is triggered to make a step leader by cosmic rays. The cosmic rays come in from space like this proton, hit a nucleus, spread and make pions and muons and gamma rays, and eventually the gamma rays decay into electrons and positrons. And those electrons get accelerated by the charge that's present in the cumulus cloud and start the step leader going. And then the step leader darts along for 50 meters, stops, because that's the length of the path of a relativistic electron, and then creates a new set of electrons, or perhaps waits for another cosmic ray. So they're really looking right now at the interaction of cosmic rays and lightning. And you have to think about lightning. Here's a thunderstorm, and it's pumping positive charge up into the ionosphere and bringing negative charge to Earth. So the entire Earth is a gigantic capacitor. And it turns out the average charge charges up the Earth to about 500,000 volts between the ionosphere and the Earth. And in beautiful bright blue skies, there's a 2 picoamp current per meter squared flowing from the ionosphere to the ground at all times. So I'm going to stop there right on time and say thanks for paying attention, and I'll set off one more lightning strike here at the end. So any questions? So I'm a planetary physicist as part of my real life, and so I had to include lightning on the other planets. and because Day was here, I had to put in one volcanic lightning slide or two. Oh, yes. So indeed, I didn't mention the electromagnetic pulse, which is just I was questioned on. And indeed, in this lightning bolt, it makes a tremendous electromagnetic pulse. The current makes magnetic fields, it makes electric fields. Any metal object around can have electric currents induced in it by the lightning. And so that metal object becomes charged at one end compared to the other end. And that's one of the reasons you don't want to be around metal objects in lightning. Okay, I will do another one. Sorry, I didn't get your question. Here's one more time on the. I got a request for one more time on the lightning bolt. That's right. So we call it under the category, as Chantal says, it's inductive effects. So the lightning induces charge. Yes. So the Science Circle always publishes my slides. But Day, if you send me patioplasma@gmail.com, or any teacher out there, if you send me a request, I will send you my slides, perhaps via Dropbox, because it's a large file. But I will gladly share my slides. Yes, Dave, that's great. I'd love to have them shared. Any other questions? Things you've ever wondered about lightning? Notice I didn't talk about ball lightning, something that's been reportedly seen by reliable witnesses, but there's no really good documentary evidence. Oh, yeah. Yay, Katana! Okay, I have one thing I promised to share with you was the link to an amazing video of of slow motion lightning. It's 7,000 frames a second image of lightning. And if someone can teach me how to show movies in Second Life, I'd really appreciate it. Then I could. Lightning just called out for movies, but I had to make a prim version instead. Okay, let's see what the questions are. Okay, so yeah, oh, that's interesting. So here's some questions. So a denser atmosphere it takes larger voltage to break down a denser atmosphere because the electrons accelerate between atomic collisions and they don't have as much distance to accelerate in the electric field when the atmosphere is denser. So in a denser atmosphere, it takes higher voltages to make a lightning discharge. And the higher voltages lead to more energetic lightning bolts. So indeed, that hypothesis that a denser atmosphere should make stronger lightning discharges is correct. This energy warping space-time, so it turns out not on a gravitational level. Nothing we can detect warping space-time. To detect warped space-time, it takes huge masses, like stellar masses. However, the gamma rays produced by lightning, when they pass near an atomic nucleus, create matter. They produce matter out of their energy. And in some ways, that's a warping of space-time, where energy of a gamma ray turns into an electron and a positron. But it's not gravitational bending. Not enough energy. Yeah, that's an amazing video. And it shows you what I was telling you, is that the lightning steps and stops. Step, stop, step, stop, until it reaches the ground, and then an incredible flash happens. And then more flashes afterwards. I'll leave the ball. So just to the left of the stage over here, I didn't want to tell you before, there's a ball. So I'll leave this up for a few days. But there's sort of a faint ball over here by my feet. And if you touch that ball, it will trigger the lightning strike and the thunder. And so I promise Science Circle that before next week's gathering, I will clean up things. And I will try to work on the slide screen here so that other people can run the slides. I apologize for not doing that yet. I'd like to have it here where people can step through the slides if they wanted to. Okay, other things I wondered about lightning, knowing that there are some things we don't know. Nobody knows. Okay, so let's see. I don't know lightning from the FF game. No, sorry, that's new to me, Ariane. And indeed, Io, as it orbits Jupiter, creates ion channels that actually trigger aurora on Jupiter. You can follow the magnetic field lines coupling Io and its plasma emissions up to the poles on Jupiter. And a bright aurora follows the moon around as it goes around Jupiter. And that who knows how much that might trigger lightning. Oh yeah, now, in fact, because of this, thank you, Ariane. Because of this lecture, I'm in at work today. I'm actually in at my workplace, which is one of the reasons that the noise environment was a little worse than at home at my desk. Because I had to give this lecture on the holiday weekend in America, I signed up to work today. And this counts as my work, yay. And then I'll be training the museum I work at, hires high school students. And we have 80 new high school students coming in to learn science and to be explainers in the museum. And I, as a physics professor, get to teach them about the physics behind the exhibits. And so that's something I do in real life. And I really believe in the educational value of virtual worlds like Second Life. And that's why it's so great to see you all from around the world interested in science coming together. Okay, so at that, I think it's probably time for me to go and have a snack, drink some tea, and thank you all. Oh, sorry, Corona. I don't know about the electric universe idea. At the moment, physicists divide up the forces of nature and into electric, magnetic as one, electromagnetism, gravitation, strong and weak nuclear, and we don't put them together yet. So I think we need all of those at the moment. Ooh, yes, that's the problem about virtual worlds that eat up your bandwidth. Okay, I'm going to head off to eat. Thank you all for coming. Thanks to the Science Circle and Q. Thank you for recording. And I look forward to this.